Hey everyone, this is part 4 of kinetics. I'm going to be talking about kinetics experiments, including details of what you would be measuring in the lab if you were an experimentalist, as well as rate laws. The reason a chemist would perform kinetics experiments is if they want to provide experimental evidence supporting or disproving a mechanism. These kinetics experiments would give you a quantitative relationship between the reaction rate and your concentration of reactants and products and how that's changing with time. You would want to start by varying the concentration of a reactant and measuring the reaction rate. If you had more than one reactant, you would want to hold the other reactant concentrations constant, keep the temperature constant, and only vary one reactant's concentration at a time. You would plot your data and discover your reaction order based on the fit of your data in your graph. This graph would give you the reaction order with respect to that reactant whose concentration you varied. You'd repeat this procedure by varying the concentrations of your other reactants, one at a time, again keeping your temperature the same. And ultimately, you would write your rate law. Whether your reaction is 0, first, or second order in a reagent could be determined by looking at a plot of the rate versus the concentration of that reactant. If a reaction is 0 order in that particular reagent, the rate will be unaffected by changing the concentration of that reactant. This would give you a flat horizontal line. If your reaction is first order in a reactant, as you increase the concentration of the reactant, your rate will increase linearly. And if your reaction is second order in a reagent, as you increase the concentration of that reactant, your rate is going to increase more quickly than linearly. As I mentioned in a previous video on kinetics, your kinetic order in a given reactant will only be first or second order, non-zero, if that reactant is involved prior to the rate determining step. Any reactants that show up only after the rate determining step will be 0 order and will not contribute to the rate law. Let's start with 0 order kinetics. This is going to be relatively rare. You would imagine a starting material going to form a product, and here I'm just assuming this reaction is 0 order in A. If a reaction is 0 order in a reactant, it's probably not a one-step reaction, and that reactant probably appears after the rate determining step. For a 0 order reaction, the rate is equal to the rate constant, not multiplied by a concentration term. The rate is a measure of the disappearance of starting material with respect to time, which can be written as negative d concentration A over dt. We're going to do a little bit of math here, and I'm going to move the dt term to the right-hand side. I moved the negative sign over as well, so I now have dA equal to negative k dt, where A is my concentration of reactant A and k is my rate constant. I call this step where I moved the time-related component to the right-hand side, separating my variables, where my variables are concentration and time. At this step, you would integrate both sides. You would be integrating your dA term from the initial concentration A0 to your concentration of A at a given time. Minus k is a constant, so I moved it outside of the integral, and then you're integrating dt from time 0 to time t. You don't need to know how to do this integration. I'll give you the outcome, which is that if you integrate dA from a0 to a, you get a minus a0. And if you integrate dt from t0 to t, you get t minus t0. Your minus k stays around because it was your constant in front of the integral. This t0, the time at 0, is equal to 0, so we're going to get rid of this term. After I get rid of the t0 term because it's equal to 0, and after I move a0 to the right-hand side, I get the equation the concentration of A is equal to negative kT plus the concentration of A at time 0. This is known as my integrated rate law, and in this case, for zero-order kinetics, the integrated rate law is of the form y equals mx plus b, so it could be fitted to a line. If you looked at a graph of a reaction that is zero order in A, and you plotted the concentration of A with respect to time, your data would look something like this. The slope of this line is equal to negative of the rate constant k, and the y-intercept is your concentration of A at time 0, however much you put into your reaction. Now let's talk about what if a reaction is first order in A instead of zero order. Here as well, I'm just considering a reactant A going on to form a product P at a rate constant K. If your reaction is first order in A instead of zero order, you will not be able to fit your data for the concentration of A with respect to time to a line. Your first order kinetics will look like a decreasing exponential. Your rate law for a first order reaction is that your rate is equal to the rate constant k times the concentration of A, where your rate is a measure of the change in concentration of A with respect to time, negative dA dt. Like I did for zero order, I'm going to separate variables, so I'm going to move my time component to the right, and I'm going to move my concentration of A term to the left. After I do this, and I move the negative sign to the right as well, I get dA over A equal to negative k dt. Now that I have all of my concentration terms on the left and time terms on the right, I'm ready to integrate. I integrate my concentration side, dA over A, from the concentration of A at time 0 to the concentration of A at time t. I move the negative k outside of the integral because it's a constant, and then I integrate dt from time 0 to time t. Here as well, I wouldn't ask you to do this math yourself, but the left-hand side is equal to the natural log of the concentration of A minus the natural log of the concentration of A at time 0. Then on the right-hand side, you have negative k times t minus t0. After getting rid of my t0 term and moving the a0 term to the right, you get that the natural log of the concentration of reactant A is equal to negative kt plus natural log of the concentration of A at time 0. This is the integrated rate law for a first-order reaction with respect to A. And this is of the form y equals mx plus b also. Instead of just plotting the concentration of A with respect to time, instead plot the natural log of the concentration of A with respect to time. For a first-order reaction in A, this plot will give you a linear fit. The slope will be equal to negative of the rate constant, And the intercept gives you the natural log of the concentration of A at the beginning of your reaction, known as A0. We're going to talk about two different scenarios for second-order kinetics. The first type is if you have two of the same molecule reacting with each other to form a product. I'll write this as A plus A going to a product P. In this case, your reaction would be second order in A because you have two A molecules involved before the rate determining step. And an example of this would be looking at the Diels-Alder reaction of cyclopentadiene. Two of these molecules will react with each other to form a Diels-Alder product. Similar to first-order kinetics, if you plot your concentration of your starting material A with respect to time, you will not get a linear fit for second-order kinetics. It will look something like an exponential curve. Your rate law for second-order kinetics is going to be that your rate will be equal to your rate constant times your concentration of starting material squared. Here as well, the first thing I'm going to do is to isolate variables. I'll move my time term dt to the right side, and I'll move this a squared term to the left. I get dA over a squared equal to negative k dt. I guess I've also moved the negative sign here. You'll integrate both sides. When you do this integration for your d concentration of A divided by the concentration of A squared, you get 1 over A0 minus 1 over A. This is equal to negative k times t minus t0. To get the integrated rate law, I'm going to keep the 1 over A term on the left, move the 1 over A0 term to the right, and then switch some negative signs. I get 1 over the concentration of A equal to kT plus 1 over the concentration of A0. Here again, my integrated rate law is of the form y equals mx plus b, so it could be fitted to a line. For a second-order reaction of this first type, where you have two of the same molecules reacting with each other, you could plot your data as 1 over the concentration of your starting material versus time. And for the second-order type 1, you would get a line of data. You could apply your linear fit. The slope here is the rate constant k. Notice I don't have the negative sign in this scenario. And the intercept is 1 over the initial concentration A0, whatever concentration of A you put into the flask. So let's say you had a reaction of A going to form a product P, but you didn't know the reaction order yet, because you're trying to figure out the mechanism. You would run an experiment where you measure the change in concentration of A with respect to time, and then you would try to plot your data 3 different ways. If you plot the concentration of A versus time, and you get a linear fit of this data, your reaction is 0 order with respect to A. For your second plot, you would plot the natural log of the concentration of A versus time. If this plot is linear, your reaction is first order in A. Then for your third plot, you plot 1 over the concentration of A versus time. If this plot is linear, your reaction is second order with respect to A. I recommend always trying all 3 fits, so you'll have 3 plots. One of these is going to have the best linear fit, the highest R-squared value, and that is the one that you should use to determine your reaction order. Now let's consider our second scenario for second-order kinetics. I'll call this type 2. This is where you have two different reactants coming together before the rate determining step. So you have A plus B reacting to form product P at rate constant K. If your reaction is first order in A and first order in B, you would call your reaction second order overall. In this case, let's imagine we have a Diels-Alder reaction, but now featuring two different components. I have cyclopentadiene A reacting with a new dienophile B to form the Diels-Alder adduct. If you plotted the concentration of A with respect to time, or the concentration of B with respect to time, it would not be linear, and it would look exponential-like. Your rate law for this type 2 would be the rate would be equal to the rate constant times the concentration of A and times the concentration of B. This rate would be equal to the rate at which A is disappearing with respect to time, as well as the rate at which B is disappearing with respect to time. In this case, the math is more complicated, and I will not show it. I will just give you the outcome of the integrated rate law. But this complicated rate law does have the form y equals mx plus b, so it can be fitted to a line. For this type of second-order kinetics, you would plot the natural log of the concentration of A divided by the concentration of B with respect to time, and if your reaction is first order in A and first order in B, this could be fit to a line. The slope in this case is more complicated. It's your rate constant times the initial concentration of B minus the initial concentration of A. And your intercept is the natural log of the starting concentration of A divided by the starting concentration of B. Notice this is already looking messier than what we've seen previously. Add that messiness to the fact that it's difficult to simultaneously track and measure the concentration of A and B at the same time, and you'll begin to think maybe there's a better way of doing this. What I will call pseudo-first order kinetics is a way to simplify your kinetics for a second order reaction, where you have a reaction that is first order in one component and first order in another component. What you do is you pick between A and B, which of those are you going to have in excess relative to the other one, and then you use at least 10 times as much of that reagent as you have of your other one. So again, let's return to A plus B goes to a product P. You could pick, let's put B in large excess relative to A. And if that is the case, although the concentration of B will go down slightly with respect to time, because it started out as so much larger, that concentration of B is barely changing. So you could say that the concentration of B at a given time t is about the same concentration of B that you started with at time 0. And the concentration of B that you started with at time 0 is a constant, equal to however much you added to your flask. So for your rate law, you would have the rate equal to K times concentration of A times concentration of B. But at any given time, the concentration of B is approximately the same as it was at the start of the reaction, because there's so much B around. So we can say our rate is approximately equal to the rate constant K times the concentration of A times the concentration of B at the beginning of the reaction that you started with. And the concentration of B that you started with is a constant rather than a variable. I'm going to move this concentration B0 term to the front side of the rate law, right behind K. I get that the rate is equal to the rate constant K times the concentration B0 times the concentration of A at a given time t. the whole term of your rate constant times the starting concentration of B looks like a constant. So you have a constant in front of the concentration of A, and now the whole thing looks first order. You could rewrite this as the rate being equal to k obs times the concentration of A, where k obs is the observed rate constant, and that is taking into account your rate constant k and your concentration of B at time 0 terms. So here's that rate law from before. The rate is equal to the observed rate constant times the concentration of A. We would call these pseudo-first order conditions with respect to A, because our B term disappeared because we assumed it was constant because we had so much B around relative to the amount of A. So let's consider 3 experiments. Assume in one experiment you have the concentration of A as 1 millimolar and the concentration of B as 10 millimolar. In the second experiment, you keep the concentration of A the same, 1 millimolar, and you have B equal to 20 millimolar instead. In your third experiment, you keep A the same, 1 millimolar again, and B starting out is 30 millimolar. So you have 3 different experiments, each with A and B present, and notice in all 3 cases, the concentration of B is at least 10 times higher than the concentration of A. So the concentration of B will be approximately constant, and we would call these pseudo-first order conditions. For each experiment, you're going to measure the concentration of A as it changes with respect to time, and you're going to plot your data as the natural log of A with respect to time. This plot will give you a line if the reaction is first order in A. Let's say that the slope of this graph is -1. That means that negative of the observed rate constant is equal to -1, or your observed rate constant is equal to +1. Because you had a graph of natural log of A with respect to time, and it was linear, we can conclude at this time that the reaction is first order in A. The reason we're going to run the following 2 experiments with different B concentrations starting out is to figure out what the reaction order is in respect to B. Let's say that you ran your reaction with the starting concentration of B equal to 20 millimolar, and remember I'm saying here as well, the concentration of A starting out was 1 millimolar again. You would measure the concentration of A as it changes with respect to time, and plot the data as the natural log of A versus time. Assume that this reaction gave you a slope of -2 instead. So the slope is more negative as the B concentration was doubled. Your slope is equal to negative of the observed rate constant, so k obs in this case is equal to +2. Now let's say you run your reaction again. Your concentration of A started out as 1 millimolar, your concentration of B started out as 30 millimolar, and in this case, when you plot your data using the same axes, you get a slope of -3. That means that your observed rate constant k obs is equal to 3. So here's a summary of my data from before. I started with the concentration of B as 10, 20, or 30, and I got observed rate constants of 1, 2, or 3. You'll want to graph your observed rate constant versus the concentration of B, and here's a representation of that data. Notice that the observed rate constant increases linearly as you increase the concentration of B. Remember that we defined k-obs as equal to the rate constant k times the concentration of B. And by this plot that we just did, where we looked at the observed rate constant versus the concentration of B and saw that that was linear, that means that the reaction is first order in B. So we previously verified that the reaction was first order in A, and then by varying the concentration of B and fitting the data, we found that the reaction was first order in B also. So our rate law is the rate constant times the concentration of A times the concentration of B. Now consider a separate reaction entirely, and let's say you got that as you increased the concentration of B in your separate experiments, and you looked at 10, 20, and 30 millimolar, and let's say in this case, instead of getting 1, 2, and 3 for your k-obs values, you got 1, 4, and 9. Like the scenario up above, start by trying to plot your rate constant versus the initial concentration of B. And notice that this is not linear. This means that the reaction is not first order with respect to B, so we'll have to try a variation on this plot instead. We can check if the reaction is second order with respect to B instead of first order by plotting the observed rate constant versus the concentration of B starting out squared. Here I've squared our values for B0, giving us 100, 400, and 900, and I'm plotting those versus our k-obs values of 1, 4, and 9. From this plot, I do get a linear fit of my data. If k-obs increases linearly with respect to the concentration of B squared, that means that this reaction is second order in B. Alright, so this video was dedicated to kinetics experiments, which essentially boil down to measuring concentrations versus time. I showed you examples of 0, first, and second order reactions and what their kinetics would look like. And in the case where you had a second order reaction, where you had your reaction first order with respect to two different reagents, I talked about using pseudo-first order kinetics as a simplifying strategy. That's it for this video. I will see you in class.